Welcome to the Tech Study channel. In the last class, we have seen about fourth question and its answer. Now we will see fifth question and its answer of triple E subject. Okay. Then fifth question is explain the biasing networks in BJT, bipolar junction transistor. First, before going to biasing networks, we will see first what is BJT, bipolar junction. In the last class also we have seen. So BJT, a device where a small current at one terminal controls a much larger current flowing through the other two terminals. Then there are two types of BJTs, PNP transistor and NPN transistor. PNP transistor contains two p-type materials and which are collector and emitter, and one n-type material, that is base. And then in NPN BJT, there are two n-type materials, collector and emitter, and one p-type material, base, that is base. In the circuits we represent like this. And a small correction here. In yesterday's class I said it is the flow of electrons, not it is the flow of current. Arrow mark indicates the flow of current. Okay, this arrow mark, emitter arrow mark. Okay, then emitter supplies charge carriers, electrons or holes into the base. Means here the emitter is there, it provides charge carriers, electrons or holes to the base. Okay, heavily doped, and base controls flow of charges from the emitter to the collector. It controls the flow of charges from emitter to the collector. Okay, like this. Then it acts like a gate for the transistor, and it is slightly doped. And collector collects the charge carriers provided by the emitter. It collects the charge carriers. The collector collects the charge carriers from the emitter through the base. Okay, then it is moderately doped. So why it is heavily doped and moderately doped and lightly doped means, to understand this we have to understand what is doping. Then doping means a process where a tiny amount of impurities are added to the pure semiconductor crystal like silicon or germanium to make better at carrying electricity, because the pure semiconductor are poor conductors at room temperature. Okay, so here doping is useful to introduce either extra electrons or holes to serve as charge carriers in the pure lattice or crystal like silicon or germanium. Okay, if it is n-type material, then the doping is used to introduce extra electrons. If it is p-type material, then the doping is used to introduce extra holes. Then why it is heavily, lightly and moderately doped means, so emitter heavily doped to supply maximum carriers. Okay, doping means what? Adding extra electrons. Here in NPN transistor, here in NPN transistor, emitter is of n type. So doping means adding extra electrons. It is heavily doped means more electrons are uh, added. So the it supplies maximum number of carriers. Okay, then the base is lightly doped and thin to minimize recombination of carriers. So in NPN transistor, the base is of p type. It is lightly doped means less number of holes are added by using doping. Okay, so why it is helpful means, when emitter supplies electrons to the base, If the base is heavily doped, then there will be more number of holes which recombines with this electrons provided by emitter. So that's why, uh, to minimize the recombination of holes and electrons, so it is lightly doped. Then we will see collector. Collector is a moderately doped to handle high voltage or heat while collecting carriers. Okay. Then we will see types of doping. In types of doping, there is n-type doping and p-type doping. Example for it is pentavalent element which has 5 valence electrons. Example, phosphorus and arsenic are added to a tetravalent 4 valence electrons element. That is example, silicon lattice. The fifth electron can't participate in the covalent bonding, becoming a free electron available for conduction. So the material is with an axis of electron charge carriers, electrons. Okay, negative charge carriers, electrons. Okay, then p-type doping, trivalent. Example, trivalent element which has 3 valence electrons. Example, boron, aluminium are added to a tetravalent which has 4 valence electrons. Example, silicon lattice. This the impurity only has 3 electrons to bond with 4 neighboring silicon atoms, leaving a missing electron site known as a hole. So the material is with an axis of positive charge carrier, that is holes. Then we will see about voltages of transistor. Okay, VCE, VBE and VBC are the voltages between terminals that determines the operating region, cutoff, active or saturation. VCE voltage, we already know cutoff means there is. So in the earlier class in the previous class I have said uh, cutoff region, active region and saturation region of a semiconductor diode, I said. So for BJT, bipolar junction diode, the cutoff active and saturation regions will be different. So so ignore that points, cutoff active and saturation region, which I have said in earlier previous class. Okay, then VC, voltage between collector and emitter, creates a strong electric field at the collector to attract the base electrons or charge carriers. VC, here is the VC between collector and emitter, creates the strong electric field at the collector to attract the electrons from base. Okay, then VBE, voltage between base and emitter. Okay, responsible for flow of electrons from emitter to base. Okay, and it must be 0.7 volts for silicon active or saturation region. Okay, then VBE, VBE is VBC is voltage between base and collector, base and collector, base and collector. So responsible for flow of electrons from base to collector. Okay, then we will come to biasing techniques. Here are the methods of transistor biasing. For simplicity and economy, the transistors should have a single source of supply, that one in the output side. Example, VCC. In the previous class, we have discussed about common emitter connection in BJT. So here we require two voltages now, at one in the input side and one in the output side. So for simplicity and economy, we are using only output side voltage. Okay, that is called biasing. Okay, so there are three ways: base resistor or fixed biasing, biasing with collector feedback method, voltage divider biasing. So in all of these biasing methods, we are using CB connection, means common base connection. Okay, we required values of base current IB, hence collector current IC is obtained from the VCC, output voltage, in the zero signal condition in these three methods. So we are finding, means we require to find the base current and collector current. Okay, is obtained from the voltage, output voltage. Okay, in the zero signal conditions. Zero signal condition means the state where no AC input signal is applied to the amplifier. The state where no input signal is applied to the amplifier, but DC supply voltage are connected to keep the transistor active. Okay, here we have seen, here we provide AC signal. So zero signal bias in the previous class we have provided AC signal here to the input circuit. So here zero bias condition, zero signal condition means the state where no AC input signal is applied to the amplifier. To the amplifier means transistor, BJT. Okay, but DC supply voltage are connected to keep the transistor active. Okay, even in zero signal condition, the collector current can't flow unless there is a specific DC base current provided by the biasing circuit. Okay, then relationship IC is equals to beta IB. The beta tells us how many times larger the current, the base current. Here the beta tells, here it is the collector current. Okay, the beta tells us how many times larger the collector current is compared to the base current. Okay, here I have explained with example. If a transistor has a beta of 100, means beta value is 100, it means that for every 1 microamperes we put into the base, the transistor allows 100 microamperes to flow through the collector. Okay, in zero signal biasing condition, the working state of an NPN BJT is defined by the interaction of base current, collector current and collector emitter voltage, VC, IB, IC and VC. Okay, So we have understand what is zero signal condition. Then the value of collector resistance RC is selected keeping in view that the VC should not fall below zero point 0.5 for germanium and 1 volt for silicon transistors. Here we have to understand carefully the value of collector resistance RC. The value of collector resistance RC is selected keeping in view that the VC should not fall below zero point 0.5 for germanium and 1 volt for silicon transistor. This is why, because to keep the transistor within the active region to prevent from saturation region, to keep the transistor within the active region to prevent from saturation region. So here they are saying we have to select the value of collector resistance RC, keeping in view that the VC should not fall below zero point 0.5 for germanium and 1 volt for silicon transistor. Okay, because if the VC is below zero point 0.5 or 1 volt, the transistor becomes in saturation region. Okay, so to keep the transistor within the active region to prevent from saturation region. How the saturation region occurs means when VC is below zero point 0.5 volts or 1 volt for germanium and silicon respectively, the saturation region occurs because the collector emitter voltage drops so low that the collector base junction can no longer maintain a reverse bias, causing it to become forward bias. So initially we have reverse biased collector base junction. So in the normal NPN BJT, the collector base junction is reverse biased and emitter base junction is forward bias. So we will understand this by using a diagram. Then collector emitter voltage drops so low. So this is the voltage VCE. So low means below zero point 0.5 and 1 volts. If it is false, it is forward bias initially and it is reverse bias. In the zero signal condition, V in is 0 and so low that the collector base junction can no longer maintain a reverse bias, causing it to become forward bias. So here the collector base junction is initially reverse biased. So it creates a electric field at the depletion layer. So that attracts the electrons gathered at base through the emitter because it is forward bias. So electrons will pressure these electrons. This will be sweeps to base p-type material. So if it is low, less than 0.5, it does not maintain a what reverse biased. Okay, here it's saying the collector base junction can no longer maintain a reverse bias, causing it to become forward bias. Means at this point both the base emitter and collector base junctions are forward bias. So turning the transistor into a closed switch where current flow is limited by only external circuit resistance. So in BJT, saturation region occurs when normally, I am saying normally, not in biasing. This is for biasing. This is normally when the saturation region occurs for NPN BJT is when it acts like a closed fully on switch, allowing max current to flow while VC drops very low. So here also the same thing happens. Okay. So here we have studied now turning the transistor into a closed switch. Both junctions become forward bias. So that's why it becomes saturation region. Okay. Both junctions are forward biased, base emitter and base collector. So to prevent from this saturation region to be in the active region, we need a VC voltage above 0 point volts for germanium and 1 volt for silicon. Okay. Then we will see base resistor biasing. A resistor RB is connected between base and positive end of supply for NPN transistor and between base and negative end of supply for PNP transistor. Here we can see RB resistor is connected between positive end of output voltage and IB base of the transistor. Then the zero signal base current is provided by VCC, means output voltage which flows through RB. The base emitter junction is positive with respect to the emitter. So the zero signal base current is provided by VCC. Here it provides the zero signal base current. Okay. And which flows through RB, means it flows from here. Okay. Then the base emitter junction is positive with respect to the emitter. The base and emitter junction is positive with respect to the emitter. So the base emitter junction is forward biased. This base and emitter junction is forward biased. The value of zero signal base current, hence collector current, can be made to flow by selecting proper value for base resistor. So the zero signal base current can be made to flow by selecting the proper value of base current. So it should be flow from here, not from here. Okay na? And current will always choose low resistive path. So by keeping in mind that these points, we will choose RB resistance. Okay, then VCC is fixed non-quality and IB is suitable value, then RB can be found directly by using Ohm's law. We can find it. Then VCC is a fixed non-quantity and IB is suitable value. Then RB can be found directly. This is the reason called fixed biasing. Okay. DC is blocked by CV capacitor and only allows AC. Here the DC is blocked here. In case of AC supply, okay. Then CE used as an alternative way for current to flow into emitter and which protects from damage of RE. It is an alternative way. So it is an alternative way to for current to flow into emitter, uh, and which protects from damage of RE, emitter resistance. So due to heavy load or heavy current flow, the RE will be damaged, so it will protect it. Okay. Then CC, it removes DC from signal which is due to fluctuation of current and provide pure AC to output. Then in case DC, F is equals to 0, frequency is equals to 0, capacitance, reactance is equals to 1 by 2 pi FC, that is equals to infinity. Then the capacitor becomes open. Okay. Then the capacitor becomes open. Then we have redrawn this diagram. Okay. Then its advantages are, it is simple as only one resistor is required, RB is required. Biasing conditions are easy to be set and calculations are simple. Disadvantages are, provides poor stabilization, means the perfection of output is very poor, and then stability factor is very low, and then biasing with collector feedback method. Before this, we have to find IB current and IC current and RB also. So by applying KVL at output side to these circuits, we get the IC, and by applying KVL on input side, we get the IB and RB also. So how we will get, then we will see here, VCC minus RCIC. Here is the VCC. On output side we are applying RC into IC, resistance into current, that is equals to voltage now. Then VC, here we have VC. Okay, VCE, and then IERE, that is equals to 0. As we know, IE is equals to IC because all the electrons of emitter will be gathered at collector only. Okay, then the current is also same, VCC minus RC, IC minus VC minus IC RE, that is equals to 0. IE is replaced with IC. Okay, then taking common IC from these two terms, then we will get this term RC plus RE minus VC is equals to 0. Then taking the formula for IC, that is equals to VCC minus VCE by RC plus RE, output current in fixed biasing. Okay, applying KVL at input side, VCC minus IB RB minus VBE minus IE RE is equals to 0. How we will get means, in input side, this is the output side, this is the input side. Okay, VCC minus IBRB minus VBE minus IERE minus IERE. Okay, then we know the formula, IE is equals to 1 plus beta into IB. Then we substituted VCC minus IBRB minus VBE minus, in place of RE we are writing, in place of IE we are writing 1 plus beta into IB. Then IB is taken common, RB plus 1 plus beta RE. Then taking the equation for IB, IB is equals to VCC minus VBE by RB plus 1 plus beta RE. Then we can write this equation for RB also. If we take this side to the right, left hand side denominator, then it will becomes RB plus 1 plus beta RE is equals to VCC minus VBE by IB. Then RB is equals to VCC minus VBE by IB minus of 1 plus beta RE. Okay, this is the required RB value to make zero signal to flow in the circuit. Okay, then we will see next biasing. Here I have said output and input, I have applied KVL at output and input for this circuit for first fixed biasing method. Okay, next we will see biasing with collector feed method, RB resistor. RB resistor is connected, one end is RB resistor, one end is connected to base and other end to collector. One end to base, RB resistors one end to base and one end to collector. Okay, then required zero signal is provided not by VCC but collector base voltage VBC. The zero signal base current is provided by VBC. Then VBC forward biases base emitter junction. This VBC forward biases the base emitter junction. Means the current flows from RE resistant to the RB resistant, then to the base, then to the emitter. Okay, then hence IB flows through RB. Okay, this causes the zero signal collector voltage to flow in circuit. Okay, then applying KVL to this same circuit, applying KVL at input side, VCC minus IB minus IC of RC minus VC minus IER is equals to 0. Here we have removed capacitors here for DC. Then VCC minus IB minus IC into RC. So here base current is also combined with collector current. So we are removing base current from the collector current. So we obtain the collector current, total collector current. So VCC minus RCIC minus VCC minus bracket of IB minus IB minus IC into RC minus VC minus IE/RE. This is here in the KVL applying at input side, VCC minus RC of IB minus IC. We are removing collector current from base current. Okay. So that we get IB current, base current. Okay. Then VBC minus IE/RE. Then we know IE is equals to 1 plus beta into IB. IC is equals to beta IB. VCC minus IB/RC plus beta IB/RC minus VBC minus 1 plus beta IB/RE is equals to 0. Here we have substituted beta IB, and the place of IE we have substituted 1 plus beta IB. Okay. Then VCC minus IB/RC plus of 1 plus beta RE minus beta RC. We have taken IB common from these three terms, 1, 2 and 3. RC plus 1 plus beta RE and beta RC minus VB is equals to 0. VCC minus VBC is equals to VC by RC plus 1 plus beta RE minus beta RC is equals to IB. So hence we got equation for IB current, required input current in collector feedback network. Then applying KVL at output side, VCC minus RCIC minus VC minus IE/RE is equals to 0. VCC minus RCIC minus VCE. Here we have VCE minus IE/RE is equals to 0. So as we know, IE is equals to IC, VCC minus VCE is equals to IC into RC plus RE. So we get IC value. The required output current in collector negative feedback network. Okay. Then the advantages. This is simple. This is simple because only one resistor is required. Provide some stability of a operating point than fixed biasing. Okay. Disadvantages: does not provide good stabilization, provides negative feedback which reduces the given which reduces the gain of amplifier. This will reduce the base current and hence collector current. Okay. Then voltage divider biasing provides biasing and stabilization for transistor. Okay. The two resistors R1 and R2 which forms voltage divider connected across supply voltage VCC. Okay, here it is supplied R1 and R2 and provide biasing. Emitter resistance provides stabilization. This emitter RE resistance provides stabilization. And the voltage drop across R2 forward biases the base emitter. Across R2, the voltage drop across R2 forward biases the base emitter. This causes the base current. So it causes the base current IB. And hence zero signal collector current is flow in circuit. Then after removing capacitors, we have added R1 and R2, we get RTH. Then RTH is equals to R1 parallel to R2. RTH is equals to R1 into R2 by R1 plus R2. Then we will see input side KVL applying. Then VCC minus RTH IB minus VB minus IER is equals to 0. VCC minus RTH into IB minus VBE minus IERE. Then we know IE is equals to 1 plus beta IB. VCC minus IB RTH minus VBE minus 1 plus beta IB RE is equals to 0. In place of IE, we have substituted 1 plus beta IB. Then IB taking common, RTH plus bracket of 1 plus beta into RE minus VB is equals to 0. We get the IB value, that is equals to VCC minus VBC by, that is VBE by RTH plus 1 plus beta RE. Required input current in the voltage divider biasing. Okay. Then applying KVL at output side. So the procedure is same. We have to IC is equals to IE, or we have done IE is equals to IC. VCC minus RC IC minus VCE minus ICRE, that is equals to 0. VCC minus VCE minus RC IC is taking common, RC plus RE, that is equals to 0. Then for IC value becomes VCE minus VCC by RC plus RE. VCC only now, this one. So here we get VCC minus VCE by RC plus RE. Because the negative symbol comes here, it will become same. Then advantages, this is excellent, this provides excellent stabilization from RE, means emitter resistance. So that's all for today's class. If you feel this video is helpful, then subscribe, like, share and comment, and then I will see you in the next class. Thank you. Bye.